Let's talk about action potentials. You studied action potentials in Bio 201. That was an important topic in Bio 201. Well, in the heart we have two kinds of action potentials. We need to distinguish them. I think the best way to start is to remind ourselves of how the neuron worked, and then we'll look at the action potential that's actually in the myocardium, in the cardiac muscle itself, and the action potential in the pacemaker, the SA node. All right? Let's go back and think about what was going on in the neuron. So remember, something had to get us to threshold. Do you remember what brought us to threshold in a neuron? It was graded potentials. So remember, on the dendrites of the neuron there were ligand-gated channels. The axon terminals of other neurons came in and released neurotransmitters like serotonin and dopamine and glutamate and GABA and so on. They would bind to the channels and then they would open. Remember, ligand-gated sodium or potassium or chloride channels that would create either EPSPs or IPSPs. Does this all ring a bell? It should. Excitatory postsynaptic potentials, inhibitory, and then all those charges were added up, and the axon hillock. And if the axon hillock hit threshold, which was negative 55 millivolts for a typical CNS neuron, then we depolarized. So it was graded potentials, therefore. Graded potentials are what brought us to threshold. Again, all those neurotransmitters on the dendrites getting summed up in the axon hillock. If we went above, we started at negative 70, the resting membrane potential. If we made it up to negative 55 threshold, then we depolarized. What kinds of channels opened when we depolarized? Do you remember? They were voltage-gated sodium channels. And I'm not going to write voltage-gated because these are all going to be voltage-gated. But just remember, these are voltage-gated, as opposed to the graded potentials were caused by ligand-gated channels, channels opened by neurotransmitters. These are channels opened by a change in the membrane potential, a change in electricity. So remember, depolarization happened, and then at some point the sodium channels closed, and then what other kind of channel opened right about the same time sodium closed? It was potassium that opened. And potassium then brought us back to where we started from, following a refractory period. So what it looked like was we had graded potentials slowly increasing until we hit threshold. So threshold, was like here. Once we hit threshold, we rapidly depolarized. Then we came down, we depolarized. Then we repolarized, and after a brief refractory period, we went back to normal. So here we have the graded potentials. Graded potentials bringing us to threshold. Then we opened the sodium channels, and then here we opened potassium channels. And then remember, how did we ever get back to normal again? The sodium-potassium pump restored all the proper ion concentrations. So that was how a neuron worked. You learned that in Bio 201. Let's look at cardiac muscle. Cardiac muscle is a little bit different. So this is myocardium itself. These are the cells that make the heart contract, all right? In this case, for depolarization, for reaching threshold, we don't actually do anything within the cardiac muscle itself. What we do in order to get to threshold is we use the pacemaker. So it's the pacemaker that causes cardiac muscle to depolarize, to reach the threshold where it depolarizes, all right? Then, once cardiac muscle starts depolarizing, there are two types of channels involved. There are what are called the fast sodium channels. That causes the initial depolarization. And then there are calcium channels. And calcium channels prolong the depolarization. So we get the initial depolarization, and then we have to prolong the depolarization. Why do we have to prolong the depolarization? We didn't have that step here in the neuron. Why do we have to prolong it? Because the heart's job is to pump blood out. So once we depolarize, we want the heart muscle to contract, but we don't want it to relax again immediately. We want it to stay contracted so that it can pump blood out. So we initially depolarize it with the sodium channels, and then we prolong the depolarization with the calcium channels, and that ensures that we pump blood out, all right? And then what brings us back to normal is potassium again. So the cardiac muscle action potential looks like this. We're just going along normal, and then suddenly when that pacemaker signal gets to the muscle, we rapidly depolarize, but then we prolong the depolarization and then finally return to normal again. So in this case, it's the sodium channels that are the initial depolarization, then the calcium channels prolong the depolarization, and then the potassium channels again bring us back to where we started from, all right? So notice we still have depolarization, then repolarization. The big difference here is in the cardiac muscle, we keep that thing contracted to make sure we pump out as much blood as possible. And that's what the calcium channels do, all right? This is why if you take a calcium channel blocker, that will lessen this. And so what does that do? That means your heart pumps less blood. That means contractility goes down, therefore mean arterial pressure goes down. That's why calcium channel blockers are prescribed for people with high blood pressure. They're one of many drugs prescribed. And in lethal injections, what do? Basically, they give you a drug. The lethal injection consists of two drugs. One is basically to paralyze you, and the other is just simply potassium. They inject you with a massive amount of potassium. What that does is that so depolarizes the heart muscle, it hyperpolarizes the heart muscle, that it can't depolarize again. Basically, you bring the heart muscle down so low, to a resting potential so low, that you can't ever depolarize again. That's how they kill you in the lethal injection. So that's the heart muscle itself. The pacemaker now. Pacemaker, weird, because how do you get the cell to fire in the first place? It's very clever. In this case, you use what are called slow sodium channels. And we'll take a look on the graph in a moment. So we have slow sodium channels, all right? The slow sodium channels are what cause the initial that's what causes us to reach threshold in the first place. Slow sodium channels are what actually brings the pacemaker to threshold so that it fires. Once it fires, it uses calcium channels to actually depolarize, and once again, just like all the others, it uses potassium to return to normal. So what happens in this case is the slow sodium channels are slowly leaking sodium until they hit threshold, all right? Once they hit threshold, then it depolarizes, then it comes back, it repolarizes, and then the slow sodium channels once again slowly bring to threshold, then depolarization, then repolarization. What's happening here is that these sodium channels are leaky. They're leaky sodium channels. So they're not ever fully shut. They don't ever completely shut. They're always just slightly open, so they're leaking. So what happens is sodium is slowly leaking in, slowly leaking in, slowly leaking in, slowly leaking in, until we hit threshold. And then once we hit threshold, we depolarize, repolarize, and then once again these sodium channels are slowly leaking sodium. So we have the sodium channels down here slowly leaking, then the calcium channels cause the actual depolarization, and then once again it's potassium channels that bring us back down to normal again. So those are the three, the neuron you studied in Bio 201. So that was just to remind you of the fact that we have to get to threshold, then we have to depolarize, and we have to repolarize. So once again, cardiac muscle, what brings us to threshold? Well, it's the pacemaker that does that. The pacemaker sends the electrical signal to the heart muscle. Once it gets there, then the heart depolarizes, and it depolarizes in two different ways. We have the initial rapid rise of depolarization, but then we prolong that to squeeze all the blood out. Potassium brings us back to normal. And then in the pacemaker, we've got these leaky sodium channels, constantly leaking until enough sodium leaks in to hit threshold. Then we depolarize with calcium and come back to normal again with the potassium. So notice it's all about sodium and potassium and calcium. Those are the big ions for the action potentials of all of these, all right? And in every case, we have to hit threshold, we have to depolarize, we have to repolarize. It's just a matter of the slight differences between them. So these are the two we need to know now this semester. I will ask you about these on quizzes and on exams. So make sure you know the basic how the cardiac muscle potential works and how the pacemaker potential works, okay? Text or email me with questions.